Okay, let's get started. Good afternoon, everybody. It's a real pleasure for me to introduce today's colloquium speaker, Professor Monica Allen from UC San Diego. Monica is currently an assistant professor in physics at UCSD. She got his bachelor's and PhD in physics from Harvard, after which she was a Urbanek postdoc fellow at Stanford University in applied physics, working with ZX Shen, where I was a grad student. That's where we overlapped. At UCSD, Monica's group focused on using cryogenic microwave impedance microscopy to look at quantum materials with a particular focus on two-dimensional materials and topological states of matter. Monica is a recipient of several awards, including the Air Force Young Investigator Award and the NSF Career Award. So without further ado, Monica.
Well, thanks very much for the introduction, and I'd like to thank all of you for coming to the colloquium today. I really appreciated the opportunity to visit and to share my work with you today. So these are the key players who contributed to this work. So on the instrumentation side, my graduate students Leonard and Chen have been building up a new microwave impedance microscopy setup at UCSD. Taiga Wang developed some of the models that have really guided our microscopy work on topological states of matter. Of course, these experiments wouldn't have been possible without access to high quality samples. So I'd like to thank the group of Andrea Young for some guidance on device fabrication. I'd also like to acknowledge insightful discussions and collaborations with theorists Tarun Grover, Dan Parker, and Yizhuang Yu, who are faculty colleagues at UCSD. Okay, so my group specializes in a scanning probe technique called microwave impedance microscopy, which can visualize the real space conductivity landscape in materials with nanoscale resolution. And I want to just start by providing a broader perspective on the applications of MIM in different domains of condensed matter physics and materials research. So this technique is very naturally suited for studying materials with spatially inhomogeneous conductivity profiles. So as you can see here, it could be used to image the evolution of a sample across a metal insulator transition by detecting the conductivity contrast associated with coexisting metallic and insulating domains. There's been some work on, the technique can be used to detect electronic states at order parameter domain walls in three-dimensional bulk crystals, such as the pyrochlor iridates. So this is work that was performed by Eric Ma and ZX Shen at Stanford University. Of course, the technique is also very naturally suited for investigating topological states of matter, which can often host very unusual spatial distributions of current flow, such as conducting modes that propagate along edges or domain walls or other kinds of interfaces. And in prior work, we've used this technique to directly visualize chiral one-dimensional edge states that propagate along the boundary of a magnetic topological insulator. So there's been some recent success within the community at high-resolution site-resolved imaging of Moiré superlattices in twisted van der Waals heterostructures by detecting the conductivity contrast between different stacking orders. And this work right here was actually performed by, I believe, by Alex Zettel's group here at Berkeley. And even more recently, there's been some really interesting work on using this technique to detect topological quantum valley Hall states in acoustic metamaterials. So this talk will focus on two classes of materials in particular, namely the family of 2D materials and topological states of matter. And while scanning probe microscopy has been very effective at visualizing quantum electronic states in 2 dimensions, my group has recently been working on extending our imaging capabilities out of plane. Okay, so if you're studying a 2-dimensional material, why would you care about 3-dimensional imaging? So this is a schematic diagram of a van der Waals heterostructure, which consists of a layered stack of atomically thin crystals, as you can see here. And even if the electrons are confined to a single two-dimensional plane of this heterostructure, a single monolayer of graphene, for example, they still do exist within a larger three-dimensional structure. And because of that, states that are out of plane can influence the behavior of electrons on a given layer. For example, surface disorder and charge traps can affect electrons that are living deep below the surface. The presence of nearby conducting layers can lead to a screening of electron-electron interactions. And there are even more exotic scenarios that are possible, such as the emergence of superfluidity in coupled quantum wells. And for all of these reasons, it's very natural to want to develop imaging techniques that can characterize the full three-dimensional environment of the sample. So in this talk, what I'd like to do is I'd like to offer a glimpse into the third dimension by resolving states out of plane, one atomic layer at a time, in a van der Waals heterostructure. And these are some of the scientific questions that motivated our work. So for example, if you have a system in multiple conductive layers, can you figure out where electrons are sitting laterally and vertically on a heterostructure? Is it possible to do layer-specific imaging of topological states? How is the surface disorder potential imprinted onto different atomic planes sitting below the surface? Is it possible to screen out charge disorder by selectively tuning the conductivity of one layer at a time? And is it possible for us to study the interplay between various topological or superconducting states with the real space disorder landscape or with the screening environment? So in this talk, I'd like to address some of these questions in a very simple test system consisting of double layer graphene. So this is going to be a fairly technique-driven talk. So I'm going to start by saying a few introductory words about the technique of MIM, and then I'll provide a quick update on our development of a dilution refrigerator microscope that opens up new gigahertz imaging capabilities in the milliKelvin regime. To demonstrate how this technique can be used to characterize quantum materials, I'll briefly discuss how MIM can be used to image one-dimensional edge modes at the boundary of a topological insulator. And then after that, I'll go into a discussion of our work on three-dimensional microwave imaging of van der Waals heterostructures. So in microscopy and in other disciplines where your data takes the form of real space images, it's natural to want to be able to quantify the amount of order or organization that there is in an image. So in the final section of this talk, I'd like to introduce a new research direction that we've recently started, which draws upon ideas from information theory to identify and quantify hidden order in microscopy images. And we're going to apply some of these techniques to study topological phase transitions in real space, such as the one that I'm showing here in this video. And I'm really excited about this research direction because it provides a new way to quantify order and entropy based on microscopy data. Okay, so our microscope consists of a very sharp metal probe that we can scan very close to the surface of a material. We can shine microwaves down to this probe via an impedance matching network, and we're going to measure the real and imaginary parts of the reflected microwave signal. So conceptually, what's happening is that the probe generates a very strong microwave frequency electromagnetic field that's confined to a very small spatial region in the immediate vicinity of the probe, and MIM is measuring the response of the sample to these high frequency fields. And if we're able to simultaneously detect the real and imaginary parts of the microwave signal, we can gain a lot of insight into the real space nature of conductivity and screening in a material. So this system is designed for simultaneous atomic force microscopy and microwave impedance microscopy. So as you can see here in this photo, our tip is mounted onto a tuning fork mechanical resonator that serves a dual purpose of providing height feedback, but also enabling AC mode measurements where we can monitor a signal that's modulated at the tuning fork resonance, and we can filter out signals at other frequencies. Okay, so this is a simplified schematic of our measurement setup. So basically, we could read out the real and imaginary parts of the reflected microwave signal using gigahertz lock-in detection techniques. Because this is a near-field imaging technique where the tip sample distance is much smaller than the wavelength of the microwaves, one can quantify the microwave response of the system using simple lumped element models where you could use a capacitor and a resistor, or you could use the sample capacitance and resistance to represent the screening and dissipation terms respectively. No, the 1 gigahertz is an external microwave source. The tuning fork has a resonance at around 30 kilohertz. Okay, so this technique characterizes the electronic properties of a material by probing the complex tip sample admittance of the system. For this simple lumped element model that I have on the slide, this can be expressed, this complex tip sample admittance could be expressed in the following, with the following equation. And the resulting microwave response curves show a very, very strong contrast depending on the local resistivity of the sample, as you can see here. Now, in prior work, I've previously used this technique to detect chiral one-dimensional edge modes propagating along the boundary of a quantum anomalous Hall insulator in a magnetic topological insulator. And in this system, the presence of topological edge excitations is manifested in a very sharp enhancement of the microwave response at the boundaries of the sample, which you can see here. Now, while this very simple lumped element model of the microwave response is very effective for quantifying the MIM response of conventional metals and dielectrics, this simplified picture can start to break down when thinking about more complex systems like topological states of matter, where the conductivity is defined by some tensor. So motivated by some of these questions, we were interested in trying to develop a more general theoretical framework that could quantify and predict the MIM response of quantum materials. And I'd like to acknowledge that this direction was really motivated by conversations with Alan McDonald about this data set right here. So this was a direction that was led by my former student, Taiga Wang. And basically what Taiga was able to do was that he was able to write down an expression for the MIM response of an arbitrary quantum material within linear response theory. And what Taiga was able to do is he was able to write down an equation that relates the complex tip sample admittance, which is the quantity that we're measuring in our experiment, with the dynamical charge density correlation function in the material. And I'm not going to go into all the details here, but if you're interested in reading about that, I've included the archive reference on the bottom of the screen. So to demonstrate a concrete application of this model, Taiga modeled the MIM response of one-dimensional edge modes at the boundary of a Chern insulator. And what he was able to see was that this anomalous enhancement of the edge signal that we pick up when the tip is positioned over the edge is a direct result of edge magnetoplasmons, which are charge density fluctuations that are propagating along the perimeter of the sample. And these edge magnetoplasmons are not new. They've been studied quite extensively, both in theory and in experiment, within the context of quantum Hall and fractional quantum Hall systems in gallium arsenide. Now, the smoking gun signature of these edge magnetoplasmons would be the appearance of a sequence of resonance peaks in the frequency domain, which you see here, which would be picked up when the tip is positioned directly over the edge mode. It turns out that the resonance frequency of these, the resonance frequency here depends directly on the Chern number, and the line width is very sensitive to dissipation along the edge. And one of the reasons why this is potentially interesting is because the unique frequency dependence associated with these chiral edge modes provides a way of distinguishing these topologically non-trivial states from topologically trivial states that might exist at the edge due to doping or band bending. Okay, so in order to be able to detect these types of very exotic topological states, it's very important to be able to do your experiments at very low temperatures. So in order to do this, my group, as well as several other groups, have really been striving to push the frontier of microwave impedance microscopy into new ultra-low temperature regimes. And in order to do this, what we did was we incorporated our microscope into a dilution refrigerator, which provides cooling down to temperatures approaching 10 milliKelvin. Our microscope, our scanning probe microscope, and all of our cryogenic microwave electronics are all integrated into this top-loading probe for fast sample exchange. And this picture here shows just a close-up view of the scanning probe tip and the sample, which is down at the bottom. And the takeaway here is that the system is designed to support simultaneous electronic transport measurements and microwave imaging measurements. So you could perform transport to probe the overall macroscopic conductivity of a device. And in addition to that, you can also perform scanning probe microscopy to get insight into the local nature of the electronic states that contribute to that conductivity. So I'm not going to go into the details of the instrumentation development here. So this is a schematic of our milliKelvin setup. I won't go into the details here, but if you're interested in reading more about it, I've included the archive reference right at the bottom of the screen. Okay, so now I'm going to move into layer-resolved imaging. So the very simplest test system for three-dimensional imaging would be a two-layer device. So this is a simplified schematic of our sample, which simply consists of two graphene layers that are independently contacted. And in addition to that, we have a graphite backgate. And the goal here is to distinguish or separate out the microwave signatures of quantum electronic states on the top layers and on the bottom, from the top layer and the bottom layer at every lateral position, x, y. So one thing that I'd like to note is that this technique is generalizable, so it's possible to scale up the number of layers, and a lot of the same concepts will apply. However, the data will become a lot more complicated. So for the purpose of describing this cleanly, we're going to start with the two-layer case. So before I jump into my results, I wanted to start by highlighting a few of the key experimental advances that came first. So there's been quite a lot of prior work in the topic of double-layer electron systems. One of the earliest and most impactful papers was this paper right here, this 1991 paper by Jim Eisenstein's group at Caltech. And basically what they were able to do was they were able to demonstrate a way to measure the electronic compressibility of a two-dimensional electron gas using field penetration measurements. And this paper really laid the foundation for a lot of future experiments on double-layer graphene, quantum Hall bilayers, and other double-layer platforms for exciton condensation. So in 2011, Emmanuel Tutuk's group from UT Austin applied some of these ideas from Jim Eisenstein's work in order to, and what they were able to do was they were able to read out the chemical potential of a two-dimensional material using field penetration measurements with a graphene sensor layer. So Emmanuel Tutuk's work basically applied these concepts in van der Waals heterostructures. So recently, the idea of using a graphene sensor layer has been adopted by the scanning probe microscopy community as well. So there's been beautiful work that was done by Mike Cromie's group here at UC Berkeley, where they were able to use a graphene sensor layer to visualize Wigner crystal states in TMD moire materials. And they were able to do this by imaging local charge accumulation on a graphene sensor. And this is some of the data. So the group of Ali Yazdani's group at Princeton also performed measurements based on a similar concept. And basically what they were able to do was use a graphene sensor layer to image integer and fractional quantum Hall states in graphene And they were also able to look at the interaction between these fractional states and impurities in the sample. Okay, so back to our experiments. So our sample consists of a 2-layer graphene device. And one thing that I wanted to note is that we're going to apply a very large magnetic field perpendicular to the plane of these graphene sheets. So each 2-dimensional layer is a quantum Hall insulator. So I just want to pause for a second and just provide a quick recap of the quantum Hall effect. So if you have electrons that are confined to a 2-dimensional plane, and you apply a magnetic field perpendicular to this plane, the electrons that are sitting in the middle of the sample will have a tendency to move in very tight cyclotron orbits, and they'll stay roughly localized. Meanwhile, the electrons that are living near the edge of the sample will be able to engage in skipping orbit trajectories, and they will be able to move along the boundary of the sample in either a clockwise direction or a counterclockwise direction, depending on the direction of the magnetic field. And this is an example, this is a simple example of what I've been referring to as a topological edge state. Now, each layer can be described by a discrete ladder of energy levels called Landau levels, which I'm showing here. And the energy spacing between these levels is determined by the size of the magnetic field. So if you apply a larger magnetic field, you're going to have a larger energy spacing between these levels. Now, the key experimental tuning knob in this work is going to be the Fermi energy, which we could tune along the energy axis. And we're able to tune the Fermi energy by applying a voltage to the backgate and also by applying a voltage between the flakes. And I'll walk through the details over the next few slides. Okay, so again, this is maybe a simplified schematic of our measurement setup. And the first thing that I'm going to show you is a plot of the MIM response of this double layer system at a fixed point. And the results of this measurement are right here. So basically what you could see is you can see a series of minima in the MIM response. And these minima correspond to these incompressible or gapped quantum Hall states. So you see a minimum in the MIM response when the Fermi energy is tuned to be in the gap between the Landau levels. And all of this behavior that we see is consistent with prior MIM measurements of monolayer graphene. So basically what we can see from this measurement already is that the MIM response of the double layer system is primarily dominated by the signal that's coming from the top layer. Okay, so before going into the rest of the data, I want to provide a very basic conceptual overview on what we might expect to see. So first, I just said that the MIM response of the 2-layer system is mostly dominated by the signal that's coming from the top layer. So let's first consider what the MIM response of the top layer would look like. In order to understand this, we need to ask how the Landau levels in the top layer are affected by the Landau levels in the bottom layer. And there are 2 simple scenarios that can describe the possible behavior. So in scenario 1, for scenario 1, the lower layer is highly compressible, meaning that it's metallic. And if the bottom layer is highly compressible, then the electric field from the backgate will be screened by this bottom layer. And what that means is that the top layer will not have a backgate dependence. So just to recap, if the bottom layer has a high density of states or it acts like a metal, then it will screen the electric field that's coming from the backgate, and the top layer will not have a backgate dependence. It's not going to see any change in the backgate. So scenario 2 is the opposite case where the lower layer is gapped, meaning that the lower layer is acting like an insulator. And in this case, applying a voltage if you apply a voltage to the backgate, the electric field from the backgate will penetrate through the bottom layer, and the top layer will see the voltage from the backgate. And what this will do is it's going to shift the Fermi energy in the top layer, as shown here. Now, if you shift the Fermi energy in the top layer, this is going to lead to a very large change in the impedance of the top graphene layer, which in turn is detected by MIM, as we just described a couple slides ago. So that's what we're seeing here. Okay, so now what I'm showing you here is a plot of the MIM response of the double layer system as a function of our two experimental tuning knobs. So the horizontal axis is the voltage that we're applying to the backgate, and the vertical axis is the voltage that we are applying between the layers. And at first glance, the MIM response of the double layer system appears to be dominated by the top layer, which is closest to the tip, and the dips in the MIM response that correspond to Landau levels in the top layer are represented by these purple bands, these horizontal purple bands that you see going across the screen. So those purple bands are the dips in the MIM response due to Landau levels in the top layer. Okay, so there's two observations that we can make just by looking at this data. So the first observation that we could make is that over most of parameter space, these Landau levels in the top layer have a very weak backgate dependence. And what it means is that under those conditions, the backgate is acting like it's mostly screened by the bottom layer. And therefore, in these places where you see that the Landau levels have a weak backgate dependence, that likely means that the bottom layer is compressible. The second observation that we can make from this data set is that these regions of very shallow slope can be interrupted by very abrupt jumps in the Landau level trajectory. So you can see that these purple bands are following what looks like a staircase pattern, where I'm labeling the steps in the staircase with these white arrows. So why does this happen? So these jumps in the Landau level trajectories arise because the electric field from the backgate is penetrating through the bottom layer and shifting the Fermi energy in the top layer. And so what that means is that at these places where you see a big jump in the Landau level trajectory, which are these white arrows, that this corresponds to conditions where the Fermi energy of the bottom layer is inside the gap between the Landau levels, meaning that it's incompressible or acts like an insulator. Okay, so this was just a kind of a qualitative overview of what causes these features in the data. All of this behavior can be quantified using the following model, which builds upon Eisenstein's work. And the main takeaway message from this is that the chemical potentials and the carrier densities in the two layers can be related directly to our two voltage tuning knobs as follows, using the following equations. Now, an interesting thing that you might notice if you look at these equations is in the situation where the carrier density in the top layer is fixed to be 0, which means n sub t equals 0, those two equations will simplify and take on the following form. So they simplify to these two equations that are here on the screen. And basically what this means is that if you were to experimentally follow the Landau level trajectory corresponding to the nu equals 0 Landau level in the top layer, which coincides with the 0 carrier density point, you can essentially directly read out the chemical potential of the bottom layer. So this provides a way to do quantitative readout of the chemical potential of the layer of the bottom layer. So now what we can do is we could map all of these Landau level trajectories, and we could put together a quantitative plot of the chemical potential of the bottom layer as a function of the carrier density in the bottom layer. And that's what I'm plotting right here. Furthermore, from this plot of the chemical potential, you can get quantitative readout of the Landau level gaps. And because the size of the Landau level gaps in monolayer graphene are known and they're published in the literature, this provides a way for us to quantitatively validate the model that we're using and check that our understanding makes sense. So furthermore, you can also take the derivative of the chemical potential with respect to the carrier density, and this gives you the electronic compressibility, which is a direct probe of many body interactions. And interestingly, in this plot of the electronic compressibility, which is this derivative of chemical potential with respect to carrier density, you get a plot that looks like this. And what this is showing is that we're able to detect signatures of fractional quantum Hall states, as well as the existence of a negative compressibility, which is a signature of strong electron-electron interactions in the bottom layer. Okay, so as a second consistency check to see if this model makes sense, we can also fully model the MIM response of the combined double layer system, and we can compare it to our experimental results. So in order to do this, we need the sigma XX, the longitudinal conductivity of the top and bottom layers. So we can map these out as a function of your top and backgate voltages, and then use those conductivities on the top and bottom layers as input parameters. And from there, we can simulate the MIM response of the double layer system. And so the combined MIM response that includes contributions from both layers is shown right here. And one takeaway message that we can get from this model is that we can immediately see that it's possible to isolate the MIM response from the bottom layer by imaging through the top layer when the top layer is incompressible. So these oscillations that you're seeing over here that I'm pointing to with my cursor, so these correspond to Landau level oscillations that are coming directly from the MIM response of the bottom layer, and we're able to see them because the top layer is tuned into a gapped or incompressible state, so we're able to image through it. Okay, so, and these features are apparent in the data, so we can see these vertical lines that correspond to the dips in the MIM response that are coming directly from these Landau levels in the bottom layer. Okay, so now that we've talked about how to just kind of set up layer resolved imaging of electronic states, there are a few questions that we might want to ask with this technique. So the first question that we might ask is, how is surface disorder imprinted onto different atomic planes that are sitting below the surface? So we've used this capability to independently map out real space charge density fluctuations by separately tracking Landau level transitions in the top and bottom layers. And the process goes something like this. So we can use the procedure that I just showed you to measure, to isolate and measure the Landau levels in the top layer. And from there, we could measure the position dependence of these Landau level dips as a function of x for a fixed value of y. And what we can get from this is we're able to map out the real space voltage fluctuations in these Landau levels. And furthermore, we can repeat this process as a function of x as well. And as a result, what we get is a two-dimensional real space map of the carrier density fluctuations in the top layer. So this is basically a real space visualization of electron and hole puddles in your top graphene layer. Now what we can do is we could do direct MIM imaging of the Landau levels in the bottom layer, and we could track the shifts of these Landau level trajectories. And from there, we can also construct a real space map of charge density fluctuations in the bottom layer as well. So what I'm showing here are essentially real space maps of electron hole puddles of the top atomic layer and the bottom atomic layer read out separately. So one thing that we might notice from this is that it appears that the geometry of the disorder potential from the surface layer is imprinted onto the buried layer, but with a strongly attenuated amplitude. And to quantify this, we can plot histograms that describe the upper and lower density distributions, or we could plot histograms that show the density distributions of the top and bottom layers. So another thing that we might want to ask is, what is the interplay between these fractional topological states and the disorder landscape? And so to be more specific, one thing that we wanted to ask is, how does electrostatic screening of the surface disorder impact the stability of the fractional quantum Hall effect? Or in other words, is it possible for us to be able to screen out the surface disorder in order to increase the stability of these fractional quantum Hall states in the bottom layer? So in order to do that, what we did was we directly probed the MIM response of the lower layer while tuning the conductivity of the top layer. And these are the results. So we see 3 different regimes of behavior. So what I'm plotting here is the MIM response of the bottom layer, and these different colors correspond to conditions where the top layer is compressible. or conductive, that corresponds to yellow, or incompressible or insulating, that corresponds to purple. So there's 3 regimes of behavior, and let's walk through them one by one. So in the first regime, which corresponds to these conditions, so this corresponds to conditions where the top layer is fully gapped, meaning that there's no screening of the surface disorder. And when the top layer is gapped or insulating, we can easily image through the top layer, and we could observe very prominent dips in the MIM response that correspond to lambda levels, the -1, 0, and 1 lambda levels of the bottom layer. So under the opposite extreme, when the top layer is fully conductive or fully compressible, what we see here is that the visibility of the quantum Hall states in the bottom layer is strongly suppressed. And this likely occurs because this highly conductive top layer is screening the field that's coming from the microscope tip, and that's reducing the contributions of the bottom layer to the reflected RF signal. Now there's an intermediate regime where something interesting happens, which corresponds to this plot right here. So this is an intermediate regime where the top layer is partially compressible, and in this situation we start to observe fractional fillings in the bottom layer. And this likely arises because the moderately conductive top layer is able to screen out surface disorder, but at the same time it's just insulating enough to allow the MIM signal to penetrate through it. So this provides so by tuning the conductivity of the top layer, we can also play with the disorder landscape and screen out that disorder landscape. Okay, so on a practical level, one thing that I'd like to highlight are a few different sensing capabilities that are enabled by this multi-layer imaging approach. So the first thing is it allows for top gating or displacement field control with imaging. What that means is that we could use the top, if we use the top graphene layer as a top gate, we could basically image states in the bottom layer as a function of displacement field. And this has been a very difficult thing to do in the scanning probe microscopy community because typically devices with metal top gates are very difficult to image because the presence of the gate blocks access to the sample for the tip. Furthermore, the ability to directly read out the Fermi energy of the bottom layer gives us direct insight into the band structure. It allows us to quantify gap sizes and also detect the presence of strong electron interactions. And this is not possible using traditional MIM. So another thing that I'd like to mention is that this device geometry can be generalized. So you could replace the bottom layer with any sample. So you could imagine replacing the bottom layer with an interesting moire system or rhombohedral graphene. And this would provide a platform for being able to do microwave imaging or local compressibility sensing with displacement field control. And for these types of moire materials, it's absolutely critical to have access to this displacement field tuning knob in order to access certain interesting correlated or topological states in these systems. And finally, as I mentioned before, the ability to do multi-layer imaging also allows you to create a tunable screening environment as well. Okay, so in the last few minutes, I want to talk a little bit about some new methods that we've been developing to extract information about order and entropy from microscopy data. So this is real space microscopy data. Okay, so physicists are often interested in being able to quantify how ordered or disordered a system is. And for people who do microscopy or for people who work in other disciplines where data takes the form of real space images, it's natural to want to be able to quantify how much order or organization that there is in an image. So for example, if you take a look at these two photographs, you can easily see by eye that the left photograph looks a lot more disordered and there's a lot more randomness there compared to the right image. And the key question that we want to ask is this quantifiable? Within the field of computer science, another way of phrasing this question is to ask how much information is contained in an image. And a mathematician named Andrei Kolmogorov proposed a very simple and elegant answer to this question, which is that the amount of information contained in an image equals the length of the shortest program or the shortest set of instructions that can reproduce all of the features of that image. And this is called the Kolmogorov complexity. And it's an idea that can be illustrated very simply in the following example. So consider the following pair of images. So the image to the left has a very great deal of disorder. It has a lot of randomness. And therefore, the set of instructions, in order to fully describe all of these details and replicate all of these features, it would need to be, the set of instructions that would describe it would need to specify the value of every single pixel. So the instructions would look something like this. Set pixel 1 to be red, set pixel 2 to be green, set pixel 3 to be pink, and so on. And it would be a very, very long set of instructions. By contrast, the more ordered image to the right could be described by a much shorter set of instructions. So in particular, in this case, all you would have to do is describe the color and the coordinates of six solid rectangles and define the checkerboard pattern, and you're done. And the key takeaway message from this example is that ordered images have shorter descriptions, meaning that the left image has a high Kolmogorov complexity, the right image has a low Kolmogorov complexity. Now, the Kolmogorov complexity is typically not a computable quantity. However, it is possible to extract it from data algorithmically using lossless compression algorithms. And this would be done using the following process. So you would start with your original image, which has a file size L. You feed it into your lossless compression algorithm, and that would output a compressed image with a potentially shorter file size. And by lossless, what I mean is that the compressed image is able to fully replicate all of the features of the original image, so no details are lost and no information is lost in this compression process. Many of you are probably already familiar with the idea of data compression. Data compression is commonly used to efficiently store pictures on your computer. And because efficient data storage and efficient image storage is so important in so many different industries, computer scientists have become very, very good at developing lossless compression algorithms that get very, very close to the Kolmogorov complexity. And so what that means is that being able to read out the size of the compressed file gives you a direct, so basically what that means is that these lossless compression algorithms can provide a quantitative measure of hidden order in an image, even if you don't know where that order is, what that order is or where it's coming from. So a natural question to ask at this juncture is, how does this concept of the Kolmogorov complexity relate to the idea of entropy? And in 1948, a mathematician called Claude Shannon proposed the idea of information entropy, which is also called the Shannon entropy, and it's defined as follows. So if you have a probability distribution of an ensemble, if you know the probability distribution of an ensemble of microstates, the Shannon entropy provides a quantitative measure of the information content following this expression here. And in physics terms, if we take X to specify the microstates of a thermodynamic ensemble, and P of X are the probabilities of their occurrence, then H reproduces the thermodynamic entropy. Now, one interesting thing is that this Kolmogorov complexity closely approximates the Shannon entropy, and these two quantities turn out to be equal in the large system limit. Now, over the past few years, a couple physicists, Paul Chaikin and Don Levine, noticed this, and they started to extend and apply these systems to quantify order in condensed matter systems, in many-body condensed matter systems. And in particular, they were doing a lot of work within the area of soft condensed matter. So essentially what they were able to do was they were able to test lossless image compression techniques to identify phase transitions in systems of active Brownian particles. So this started to establish this as a technique that could potentially be useful in physics for the detection of phase transitions and for the identification of order in images. Now, more recently, my colleague Tarun Crover has also been testing this algorithm, lossless compression algorithm on the icing model, and he's also been thinking about applying this to better understand quantum gas microscope experiments in the field of AMO. But in my group, we've been thinking about trying to apply these ideas from information theory to better understand the nature of phase transitions in quantum materials. So when applied to scanning probe microscopy images, we want to ask things like, can we use this approach to distinguish between different classes of phase transitions? Are we able to quantitatively extract critical exponents near the transition? And can we start to tease out information about the entropy and map out its evolution across the transition at milliKelvin temperatures? Okay, so to illustrate this in a simple test system, I'm going to return to the idea, this topic of quantum Hall systems. So I'm returning to the topic that we discussed earlier in this talk. So as you recall, if you take a two-dimensional sheet of electrons with a disorder and you apply a magnetic field, this is the resulting density of states as a function of energy. So you get a ladder of Landau levels that are broadened by disorder. And all of the states are localized except for a single state at the center of the Landau level. And as you might recall, the key experimental tuning knob in this experiment is the Fermi energy. So the Fermi energy allows you to control the phase transition across these Landau levels. And this shift in the Fermi energy can lead to a change in the impedance of the graphene, which we can detect experimentally using MIM. So if we were able to repeat this process in real space, what we could do is track the evolution of the sample across the phase transition. And we're going to get a movie, so you'll get a series of MIM images that looks like this. And we want to see if we could tease out some information from these images. Okay, so before applying this to all of our data, we wanted to first test it out on a simple percolation model, which is shown here. So this is basically an animation of a simple percolation model that we had developed. So basically in each frame, we add a bunch of black pixels in completely random locations with the only restriction that you cannot add a pixel to a site that's already occupied. Now a video like this showing this percolation transition can be broken down into a series of frames, which I'm showing at the bottom of the screen. And so to test this approach, what we could do is consider each of these frames of the video one at a time. So we're going to take frame one, we're going to feed it into the compression algorithm, and this is going to output something called the computable information density, and that's simply defined to be the length of the compressed data file divided by the length of the original file. Now we can repeat this for frame two and repeat this process for every single frame in the sequence. And what we can get from this is a plot of the computable information density, which is a proxy for entropy, and we could map out its evolution as a function of the driving parameter and see how it evolves across these transitions. And what we see from this simple test model is that there's a maximum in the entropy near the percolation transition, which is tentatively what we would expect. Now I want to contrast this with the alternative approach, which is to calculate the Shannon entropy directly following the equation that I introduced earlier. So how would you calculate the Shannon entropy directly? So if you have a given frame with a fixed number of black pixels, say, what you would need to do is you'd have to repeat this measurement a very large number of times to obtain the full probability distribution for every possible configuration of that number of black pixels on a white grid. And as you might imagine, coming up with this distribution might be a very, very time-consuming process. But if you were able to do it, that would allow you to directly measure the Shannon entropy. Now, if you wanted to map out the evolution of the Shannon entropy across a phase transition, you would have to repeat this process for every single frame in that video. And as you might imagine, if you have a real system, obtaining the probability distribution for so many states can be very, very time-consuming or impossible. And so this motivates our use of this computable information density as a proxy for the Shannon entropy when analyzing two-dimensional images of systems. Now, another question that we wanted to ask is it possible for us to quantitatively differentiate between different classes of transitions using this lossless image compression approach? And so to test this out, just for fun, we decided to apply it to two different types of growth. So the one at the left is called Eden growth, which simply means that each set of black pixels in each frame is only attached to the boundaries of an existing domain. The one on the right, just for comparison, is our simple site percolation model. And the interesting thing that we noticed from this is that if we feed all of the frames of these videos into the lossless image compression algorithms, we get the curve that shows the evolution of your computable information density as a function of your driving parameter look very, very different for these two different types of phase transitions. So it would be interesting if we were able to better quantify, use this as a quantitative tool to classify different phase transitions. Another thing that would be interesting is if we were able to extract critical exponents near these transitions, and based on some of our preliminary work, it seems like this might also be feasible. So I'm just going to quickly return back to this topic of the quantum Hall transitions. So what we do is we start with our two-dimensional data set. We map our data onto something called a Hilbert curve, which is a space-filling curve that preserves locality. That outputs a one-dimensional string, and then we feed that into something called an LZ77 compression algorithm, and that's how we're getting the computable information density from our microscopy data. And if you do this for the quantum Hall data, what you tentatively see is you see a peak in this CID, which is a proxy for entropy, right at the quantum Hall transition, which by comparison is marked by this change in the MIM contrast between compressible and incompressible states. There's a few details that I'm going to skip over. So it's possible to try to discretize the data along the color axis in order to extract information about domain sizes and map like the divergence of the correlation length across these transitions. I don't have time to go into all the details, but here's kind of a summary of what our results are. So this is a plot here. This is a plot of the computable information density, and this is a plot of the correlation length as you ramp the system across a quantum Hall transition. And interestingly, you can see this very significant enhancement of the entropy across these phase transitions, as well as the divergence of correlation length. So we can already tell that this method could be a very useful way of detecting the presence of phase transitions and potentially also quantifying order and maybe teasing information out about the entropy as you go across a phase transition. So one other small thing that I wanted to mention is that if you have a sufficiently clean graphene sample, it's possible to resolve fractional quantum Hall states in addition to integer quantum Hall states. And this is a newer direction that we've been pursuing, but we've been able to visualize small puddles of fractional states. This is an example of 4/3 puddles, and we're able to track their evolution across fractional quantum Hall phase transitions as well, and we're very interested in applying similar methods to understand fractional quantum Hall transitions. And then finally, another thing that we can do is we can also create these movies that visualize the real space evolution of an edge state across a topological phase transition. And so that's what's being shown here. So this is showing the evolution of your edge state profile as detected by the MIM response as you tune your Fermi energy across these quantum Hall transitions. And so this is another thing that we're also trying to understand a little bit more quantitatively using the analysis approach that I just talked about. Okay, so that brings me to the end of my talk. Let's see. So I'd like to acknowledge all of the people who contributed to this work, and I'd also like to acknowledge my funding sources, and finally, I'd like to announce that I do have some openings for postdocs. So please contact me if you're interested in applying. Thanks so much for your attention.
Okay, thanks a lot for a really great talk, and talk for some questions. Yes, sir.
So you were asking about the double layer device, and what was the question about the device?
So how do you do the screening from the top graphite gate?
So are you asking how we're able to image through the top gate, why the top gate doesn't kind of screen the field from the tip? Yeah, so that's a really, really good question. So basically in these two systems, you have a kind of a ladder of discrete energy levels, and you can tune the system to be compressible or incompressible by tuning the Fermi energy in each of these layers. And so basically what we could do is by tuning a given layer between an incompressible, tune it from incompressible to compressible, we can essentially modulate the vertical transmission of microwaves into the structure. So if you take the top layer and you fix it in an incompressible state, that allows the transmission of the microwaves vertically, and then you can start to detect states on the layer, the next layer down. Whereas if it was if the top layer was a compressible state, then you're going to be limited to only measuring that top layer. Now you can generalize this to systems with even more than 2 layers. So if you had like a 3-layer system and you only wanted to look at the 3rd layer and you wanted to only read out states in the 3rd layer, then you can kind of control the transmission of microwaves layer by layer this way. Does that answer your question?
Well, are there any other questions from the cheap seats? Yes.
Could you play the movie again?
No, I called on the
I'm sorry.
young woman behind you.
I'm sorry.
Oh.
It's okay.
So from my understanding, if we have a multi-layer heterostructure, so we also like turn one of the layers into compressible, that explain the
Yes, I mean, so one of the key requirements for this to work is that you have a system of layers where each of the conductive planes is independently contacted. If you have a multi-layer system, I don't know, like some sort of complicated, twisted heterostructure with many, many layers, it would be much more difficult or impossible to apply the technique to do layer-resolved imaging for that structure. Was that the question that you were asking, or? Yes, that's also a good question. So of course, the signal size will decay as you increase the tip sample distance. So that's one thing that will limit it, yeah.
Please. Yes. No, go ahead, and there's a person behind you who's next. Go ahead, Chris.
If you were allowed, if you could measure with a scanning probe and attach a terahertz pulse or an infrared pulse, would you be able to measure anything different? So what would you measure?
Yeah, that's a very good question. Yeah, I guess if the pulse perturbs the system in a way that could be detected by the MIM response, then that's something that we could potentially measure. But yeah, it's an interesting question. It's not one that I've thought about very much.
Can I ask a related question? Also, in this type of spectroscopy, what about having a broadband source exciting this tip, and then measuring the photoconductivity in some remote electrodes, where then by scanning, you would get some kind of image as well. And also, in that kind of experiment, if you're not measuring reflection, you don't have sort of impedance matching and narrow band. You could kind of excite, a very broad range of photon energies.
Yeah, that's a really interesting suggestion. And I think, as you pointed out, one of the big limitations is our impedance matching, because that restricts us to like higher harmonics of some resonator. Yeah.
Yes.
Yeah, I'm curious, do you see any resonance of the carbon-13, since you're doing like basically similar to an NMR type measurement?
No, I don't think that we're detecting that.
Yes. Last question.
You had a movie about 15 minutes ago.
Is it this one? Is it this one?
About 15 minutes ago.
Oh.
I think the next showing of that would be a matinee tomorrow.
This one, maybe this one here? Yeah, so sorry, it was just meant to be kind of a summary that shows the type of data that we collect. So we get a sequence of real space images as a function of a driving parameter. I know that there's a lot of details there that I didn't describe though.